All right, welcome to our chemistry lecture. Um, I just want to preface this one by reminding everybody that on the syllabus and um, on the course description online, they highly recommend that you have at least one semester of college chemistry under your belt, or at least like AP chemistry from high school, before enrolling for this course. Now, if you haven't, it's not a huge deal, but it's just going to be a steeper learning curve for you. And so don't expect this chemistry lesson to be like everything in depth. It's really just supposed to be more of a review so that we can build upon it larger principles. So let's get started. This is a periodic table of elements. It's the way that it's arranged in order has a lot to do with the structure of the atoms that it's representing. Let me just orient you to each square is going to be responsible for one element. And the number in the upper left-hand corner of each element, so for hydrogen up here, it's 1. For helium over here, it's 2. That number represents the number of protons in the nucleus for those atoms. And protons are positively charged particles in the nucleus of the atom. There's also neutrons in the nucleus of the atom that will add weight to the atom. They'll make it heavier, but they don't have a charge. They're a neutrally charged particle. And then the number of protons in the nucleus is what gives the atom its identity and its personality. And so we say that because every atom is born into this universe. Every atom, what's crazy is like every atom that's on your computer is made out of, every atom that your body is made out of, every atom that the planet is made out of was actually born into existence in a nuclear fission reactor inside of a star. And so each one of these had its birthplace inside of a star. And the reason why is because a star is the only object in the universe that has enough mass and enough energy to be able to add protons to the nucleus of an atom. So once an atom has been formed and it's got like, if we're looking at carbon over here, it's got 6 protons in its nucleus. Once that atom's been formed, we cannot on this planet, on the planet Earth, like with all of our science and all of our um, knowledge about chemistry and energy, we cannot add another proton to that nucleus. We just don't have the power. If it was in the core of a star, possibly, we could add a few more protons, maybe turn it to iron or something. But yeah, as far as we're concerned, as soon as it's born into the universe, it just stays with that number of protons. So the number of protons is what gives the atom its identity. So if I say, hey, I got an atom here and it's got 8 protons, you could look at the periodic table and say, oh, okay, well, that's going to be oxygen. And so every atom is born into the universe with the same number of protons and the same number of electrons. So protons are positively charged particles, and then electrons are negatively charged particles that surround the nucleus of an atom. They have a spin, and we're not going to get into that too much. If you take a chemistry class in college, you talk about electron spin. And what's interesting about electrons is that they don't have to stay with the atom that they're born into the universe with. So electrons are sort of like they hang out, around the outside of the nucleus, and they have orbitals and stuff. And so there's the same number of electrons as protons. So like if I was looking at carbon, I could say, oh, there's 6 electrons and there's 6 protons. But the electrons can leave or they can come. So carbon can gain an electron, carbon can lose an electron. Same thing for oxygen. Oxygen can gain an electron. Usually it doesn't lose it. And I'll show you why on the next page here. Okay, if I can get there. There we go. Okay, so what we have here is we have a hydrogen atom here on the left and a helium atom here on the right. And on the left side of the chart here, we have period 1, period 2, period 3. And so this is talking about the electron orbitals. So electrons orbit have probability fields around the outside of an atom, and electrons can gain energy, they can give off energy, they can jump orbitals. So electrons have a lot more autonomy or freedom of movement around an atom than, say, the protons. So if I say, oh, this atom has 6 protons, you'd be like, okay, that's carbon no matter what. But if I say this atom has 6 electrons, you would be like, well, it could be any number of atoms because it could have either gained or lost electrons. So anyways, the first orbital around the outside of an atom has only room for two electrons. And so if we look at the first element on the periodic table of elements, it's 1 proton in the nucleus. That would be the hydrogen, right? 1 proton, and with 1 electron circling around. So hydrogen is an interesting molecule. I would say or atom. It's as interesting as water because water has a variety of properties that helps it to support life, which we'll talk about in a little bit. But what's very interesting about hydrogen is able to lose its electron at any given point. And so if hydrogen loses that electron, if that electron jumps off of hydrogen and say lands on an oxygen, then this hydrogen is literally just 1 proton floating around without an electron. And that makes it incredibly corrosive, meaning like that proton floating around is desiring or wishing that it had an electron to kind of balance it out in terms of charge. And so it'll travel around and rip electrons off of other things and destroy them in order to get them. You might say, okay, well, what does that mean in the bigger context of things? When hydrogen loses its electron and it becomes that proton, that makes the solution that it's in, like if it's in a water-based solution, that makes that solution more acidic, right? And so acidity, or the acid nature of a solution, is based upon the concentration of just these free hydrogen protons floating around in a solution. So that's why when you pour acid on metal or something, metal is very uh, metal has no problem giving up its electrons, right? That's why it conducts electricity so well, is it can just take an electron and pass it on down the line, right? So that's why if you pour some acid on a metal, you get a crazy reaction because the hydrogen protons want those electrons and the metal wants to give them up, and so boom, it happens quick. So anyways, that first orbital is filled up by 2 electrons. So once it's full, it's full. And once the orbital is full, if there is the same number of protons as electrons, then we would say that that element is part of this royal family of elements that doesn't react with anything else. It's happy. It's got an outside orbital that's full, and the number of protons matches the number of electrons. So it's good to go. Now, when we talk about the next orbitals, this is an oversimplified version, but it's going to work for what we're going to do in biology. When you look at the next orbital will say wants to have 8 valence electrons, and every orbital after that will just say it wants to have 8 valence electrons. And so as it fills up, right? So as we look at lithium, and I'll go back so we can see lithium, it's over here, right? So it's already got the one orbital, right, that only requires 2 electrons. That one's full. And now it's starting the next orbital in this next column here. And it's only got 1 electron. And so if we look here, there's lithium's 1 electron in that next orbital. And then look at carbon. Carbon's got 4 electrons in there. So let's count. Let's go back. There's carbon. So that has 1, 2, 3, and 4 electrons. That means carbon wants to get 1, 2, 3, 4 more electrons so that it's over here with these noble gases, where each one of these noble gases has the same number of protons as electrons, and its outer valence, its outer shell, is full of electrons. So these ones don't react. They don't play with anybody. They don't play well with anybody else. So the way that I've described this in the past is I've said, like, if you're ever a kid and played with action figures, probably speaking more to the boys than the girls, but girls use, they have their own sets of action figures, if you will. So if let's just say, for instance, you want to collect, you're a collector and you want a whole set of action figures. Well, the number of electrons that you have in your outer valence is kind of like how many action figures you have in your set of like out of the whole set of action figures. So let's say you're collecting like the Avengers action figures, right? And you've got Hulk, you've got Iron Man, and maybe Black Widow, but you're missing, like maybe, I don't know, Captain America, or I'm gonna feel really dumb here if I can't think of them all. Captain America, or I know everyone's shouting at me right now. It's that one. So, anyways, like if you're collecting action figures, you want a complete set, but you don't have a complete set. So, what you'll probably do is you'll go look for somebody else that has the action figures that you're missing, and you're going to band together with them, and together you can play with a full set of action figures, right? So you would, if you only had 3 out of the 5 Avengers, right, you would say, well, I just need 2 more, and I need these 2 more Avengers. You would go find somebody that has those 2 Avengers, and you would pair up with them. You'd form a little circle, and you'd have a little play date, and you'd be like, hey, we got all our action figures, we're having a good time. And so that's essentially what elements do. That's how they covalently bond to each other. Is you have something like carbon, and carbon's got 4 out of the 8 action figures that it needs. It can go find 4 hydrogens, which each have 1 action figure, and say, hey, come join me with your action figures. So hydrogen comes on over and they join together. And now you have carbon in a play circle with 4 hydrogens, and they have a complete set of action figures because they have 8 total valence electrons. And so we can see that when these things start bonding together. So once an electron orbital is full of 8 electrons, if you gain another proton, you have to gain another electron, right? And so that next orbital will start to fill up. And we see this with things like sodium and silicon. And so that's like the next level. So if you look like, I went the wrong way. So period 1, right? That's like this first group up here, hydrogen, helium. Period 2, right? There's going to be 8 elements there, right? Representing 1 proton, 1 electron being added every single element as we climb. Then that third period is going to be the same idea, right? So it's going to be the next orbital, the third orbital, and it can collect 8 electrons as well. Now, when we get into these next orbitals down in the 4th period and 5th period, right, we start to add some stuff in the middle. That's for another class, you guys. That's not for this class. Okay. So what's interesting about electrons is that they can actually gain energy from their environment. So if we're looking here, we got the nucleus of an atom, you've got your first period, second period, third period, right? If an electron gains energy, like if it absorbs energy in the form of, if you put something out in the sun, right, it gets warm. Well, that's because the sunlight is being absorbed by the electrons that are in the material of that object that's in the sun. And then when those electrons start to cool off, they'll release some of that energy that they absorb from the sun in the form of radiant heat, just like they absorbed it. And so electrons can jump orbitals. So they can be in a middle orbital, and then they absorb some energy, and then they jump to a higher orbital for a while until they give that energy off in the form of heat radiation. So electrons can do a couple of things, right? So we know that electrons don't have to stay with the atom that they're on, right? They're kind of like a set of action figures. And so every atom wants to have 8 whatever individual action figures, or 8 electrons. We know that they can change energy levels so that they can absorb energy and climb to outer orbitals. So the further out from the center of the atom they are, the higher amount of energy they have. They can drop down into lower orbitals by giving off energy. It's about the essence of electrons. Okay, so like I was saying, atoms like to have a complete set of action figures. So here's an example of, take oxygen, right? So oxygen's first period has its 2 electrons in it. It's got its nucleus, which has protons and neutrons, as it's just shown by a yellow blob. And then its outer orbital has 1, 2, 3, 4, 5, 6 electrons, which means that it wants 2 more electrons. So if you take hydrogen, which has 1 of those action figure electrons, and another hydrogen, which has another action figure electron, it will covalently bond. And so when we think about covalent bonding, it's where atoms collectively agree to have like a little play circle and share their outer electrons, so that all of them are playing with a complete set of action figures. And so that's kind of what oxygen's doing here. Now what you'll notice is that oxygen is only sharing one electron with hydrogen, which makes hydrogen have its full first period, which only requires two electrons. So oxygen is only sharing one electron with hydrogen in each of these cases. And then that leaves two lone pairs over here of electrons on oxygen, which is what gives oxygen its overall negative charge on one end of the atom, which means if you think about like a magnet, right? Magnets have like a negative pole and a positive pole. That means this side of oxygen is going to behave like the negative pole of a magnet. And we'll talk a little bit more about that. So that's covalent bonding. So when atoms share their electrons, it's called a covalent bond. When they share them equally, it's called a nonpolar covalent bond. And this is due to atoms having the same electronegativity, which we're going to talk about in just a second. Okay, so like I said, sometimes atoms will single bond to each other. So hydrogen can also find another hydrogen and bond to it. And so they'll both be playing with a complete set of first period action figures where they only require two to be happy. Oxygen can bond to oxygen, so they can actually form a double bond where oxygen shares one, the other oxygen shares one of theirs, that forms one bond, and then same thing happens again, and you'll end up with a double bond. And that's kind of oxygen gas. That's what we breathe in every day. Water, same idea. Two hydrogens join up with oxygen to give it its full valence of 8. Methane, like I said, carbon has 6 action figures. Whoops, sorry. Carbon actually has 4 action figures, so it needs to make 4 more bonds, and so it'll do that with hydrogen, and that's how we get methane. And so we'll see these a lot. We won't see hydrogen that much, but we'll see water, oxygen, and I'll use methane quite a bit in the future. So electronegativity, what is it? Well, if you remember, I said that all atoms, like the number of protons in their nucleus, give them their identity. So like that's what atom it is. If it's 1 proton, it's hydrogen. If it's 2, it's helium, right? But the number of protons also gives that atom its personality. So every atom is going to have its own personality, and by that I mean if if the atom is very close to having a complete set of action figures, it's going to get really aggressive about getting that last action figure. So you can imagine, like, you know, when people played like Monopoly at McDonald's, and they'd get like 2 out of the 3, you know, like little sticker cards. They would be like eating Happy Meals every day just to get like to see if they could get that last one. So it's that same idea, is that it changed their personality and behavior where they were like trying to get it more aggressively, right? And so it's the same thing with atoms. They have this personality thing where if where did I go? There we are. Okay. Where if they're very close to having a complete set of action figures, they will aggressively try to steal electrons from other atoms, right? In order to feel like they're there, that they have that complete set. And we call that personality flaw, if it's a flaw, we call that personality trait electronegativity. Okay, so some atoms are going to have more electronegativity. They're going to want to pull or hold on to those electrons more than other atoms, right? Um, what this does is, so like if they're in a covalent bond, right? Um, if oxygen's really close to getting its set of 8 electrons, and hydrogen comes along and 2 hydrogens donate their electron to this play circle, oxygen's going to hog the electrons or hog the action figures more than hydrogen. So oxygen is going to pull those electrons towards it. It's going to keep the action figures closer to itself. And this leads to an unequal sharing. And so that creates a polar bond. And so one atom will become more negatively charged in that molecule than the other atoms. And because it's pulling the electrons towards it more often, that means it leaves behind more protons on the other atoms than electrons. So in the case of oxygen and hydrogen, in the case of a water molecule, because hydrogen only has 1 electron, when oxygen's pulling that electron towards it, that leaves that positively charged proton hanging out. And so the water molecule itself has a positive end where the hydrogens are and a more negative end where the oxygen is. And so it becomes almost like a magnet. And we call that magnet, um, the magnet is called a dipole, right? But the bond is called a polar covalent bond. So remember, Non-polar covalent is where they share electrons equally. The charge, the electron charge is spread out evenly over the molecule. But a polar covalent bond is where it's polar. It creates a dipole or a magnet. So that means one side is more electronegative or more negative, and the other side then would have a more positive charge. Okay. And so we can see this desire or affinity for electrons uh, overlaid. We can overlay the electronegativity scale like we could say this is like a personality spectrum, right? And we can see that as you go from left to right on the periodic table, and as you go from bottom to top, you increase in terms of your aggressiveness for electrons. And so things that are bonded to oxygen, nitrogen, fluorine, chlorine, right? Those things that are bonded to these elements are going to lose their electrons to these elements, meaning that they are going to form polar covalent bonds with those elements. Okay, and we'll see plenty of examples of that. So here's how we would draw this. If it was a water molecule. So we've got oxygen, we've got its lone pair of electrons, right? It's pulling the electrons towards it. So the end of oxygen, the oxygen end of the water molecule will have a more negative charge, whereas the positive end of the water molecule, where the hydrogen protons are just hanging out in space, is going to have a more positive, and that creates sort of a magnet type molecule. Now, another type of bond, so we've talked about nonpolar covalent, we've talked about polar covalent. Another type of bond we run into often in biology is ionic bonds. And so when you have two elements that are bonded together, but they're pretty different in electronegativity, like almost opposite, if you will. If you were to drop that into water, the water is going to separate those two, the two atoms from each other, and create two ions. Okay, and this is why we call this an ionic bond. I want to go back here and just kind of point this out. So we were looking at sodium chloride, right? So notice sodium's over here on the far left side of the periodic table. Na, or natrum, is the Latin word for it. Natrum or sodium is over here. And then you've got chlorine is over here. And you'll notice the difference in their electronegativity is so great that when they are exposed to water, right? When they are exposed to water, sodium's just going to leave its electron on chlorine, and chlorine's going to run around like it's super happy. So sodium is actually going to end up with a positive charge. Think about it, right? Every atom is born into the universe with the same number of protons as electrons, same number of positive charges as negative charges. If sodium gives up one of its electrons when it's dropped in water, then sodium becomes overall positively charged. It becomes a cation. And so a cation, and the charge on a cation, is determined by how many more protons than electrons it has. So because sodium has one more proton than electron, because it gave up its electron, it's going to have an overall net positive charge of 1. And so we just put a plus sign there. And chlorine, the same thing. So chlorine has an extra electron. So now it's out of balance, meaning that it has an overall negative charge. And we call that the anion. And the charge on an anion, the negative charge on an anion, is determined by how many more electrons than protons it has. Right? And that's how we get ionic bonds. And so this shows you why, this image, next image shows you why sodium chloride or table salt will dissolve in water. It'll bond together and form a solid when it's dried out. But when you drop it in water, the negative ends of the water molecule, right, those oxygen ends of the water molecule are attracted to now the positively charged cation, sodium, right? So they orient themselves towards it, whereas the positively charged tails of the water molecule are attracted to now the negatively charged anion of chlorine. And so you can see how these molecules and elements are behaving like magnets. Molecules are magnets. I'm serious. Okay. So here's a couple other properties of water. Water is a pretty cool thing. Because water is like a magnet, it can stick to itself, just like magnets can stick to each other. Cohesion is where that property comes from. So you see cohesion, or an example of cohesion, when you take a glass of water and you fill it above the capacity of the glass, and it kind of forms this like bubble over the top. That's because of the magnetic properties of water sticking to itself. Now, water can also stick to other polar surfaces. So if it's something that like has a static charge, water will be attracted to it. So there's an experiment where you can take like a glass of water, you can take a string of yarn, which is a polar surface because it's got, like yarn is kind of staticky. You can drop it in the water and then put the other string of yarn into another glass higher than the one on the bottom, and the water will climb up. It'll literally climb up the yarn into the other glass, and that's called adhesion. Another thing that water does that's unparalleled by any other molecule is that it actually becomes less dense when it gets colder. And that's only to a certain degree. So, like molecules, and we'll get to this in our energy lecture next unit. But every material thing in this universe, every atom, everything that you can test for, it has a warmth to it. It has a thermal energy. Like I could shoot a temperature gun at this water bottle on my desk. I could shoot a temperature gun at anything, and it would kick me back a temperature, right? Somewhere between 0 and 100 degrees, or if it's in the summer here, 150 degrees, right? But that's measuring the thermal energy of those things, right? And if we cooled those objects off to absolute zero, the molecular motion inside of them, there's a vibration to everything that has heat in it. The molecular vibration, if we cooled it off to absolute zero, would completely stop, right? And so what ends up happening is as you cool things off, their molecular motion, microscopic motion, it's just a little vibration, their molecular motion slows down, and the things get closer and closer together. So normally as you cool something off, it shrinks. And you know this from experience, right? Put something in the freezer, it kind of shrinks up, right? Air becomes less dense as it gets cold. Or sorry, air gets more dense as it gets cold. So if you were to take like a Ziploc bag and fill it as full as you can full of air, and then go stick it in the freezer, the bag would collapse and lose air. Or in the winter, sometimes you have to put air in your car tires. That's because it's cooling off, and so the air becomes more dense, and then it's not filling out the volume of your tire as much. But here's the weird thing, right? Water actually becomes less dense when it gets cold. So as soon as it freezes, water spreads out. It creates this lattice-like structure that, because of the orientation of the water molecules, right? It builds this lattice-like structure. I can show you here. So these water molecules will start to stack and form a lattice-like structure, which actually creates a less dense object like an ice cube, and it floats. Okay. And then water also, so there's these other properties. So water also acts like a solvent. Um, and what that means is that you can dissolve things in it. So when we say something's a solvent, that means you can dissolve other things in it. So when we take water and we mix it with a solute, so that's something that will dissolve in a solvent, then it becomes a solution, like salt water. So we'll see this a lot. Like your entire body is a solution because your body's made mostly of water, right? You have ions and proteins and carbohydrates and all kinds of stuff dissolved in that water. And so your body is a type of solution, right? A complicated one by all means, right? Now, we also said that water can have various pH levels. And if you know pH, if you're into pool chemistry, right, you know what pH is. But we calculate pH based on the properties of water. So remember, water is 2 hydrogens and 1 oxygen bonded together. If we were to add hydrogen protons to that water and just slowly add those protons to water, we would slowly lower its pH down to become more acidic. And so as we're adding those protons, it becomes more acidic. So the middle of the scale, of the pH scale, number 7, that's where you have 2 hydrogens for every oxygen. You can think about it like that. You have 2 hydrogens for every oxygen, and if you have that ratio, you're at a pH of 7. As soon as you increase the ratio of hydrogens to oxygens, that's when you lower the pH, and that's when the pH becomes more acidic. Now, on the other side of that, right? So if you want something to be more basic, you have to increase the number of OH groups, right? So that's missing that hydrogen proton. It's almost as if somebody's taking away some hydrogen protons and there's OH groups or hydroxyl groups floating around. And so the more hydroxyl groups you have relative to the water molecules, that's where your pH starts to go up. And that we would call that basic. Okay, so that's just some properties of water. And then one last thing is buffers. So buffers are a type of solution. So it's stuff that's dissolved in water that's designed to help stabilize the pH of water, whether that's the pH of 7, pH of 5, pH of 6, right? The buffer is designed that if you add acid to that solution, like you keep adding hydrogen protons, the buffer will eat up those hydrogen protons. They'll bind to that buffer and they won't change the pH. And same thing for like if you have something that's basic and you have more hydroxyl ions or hydronium ions, OHs. If you have more of those and then in a buffer, and you start to add more OHs to it, the OHs will stick to the buffer and they won't change the pH. And so buffers can help stabilize. And your bloodstream is a buffer. Your bloodstream has a constant pH that changes very little despite what you eat and drink. Okay. All right. So let's talk about van der Waal interactions. This is the idea that molecules of the same type can attract or repel each other. Typically, when we look at polar molecules, it makes sense that they can attract each other because they're behaving like magnets. But nonpolar is where it gets to be a little bit of a head scratcher, because nonpolar is where they're passing the electron back and forth from atom to atom, and it's not changing their overall charge, right? So they're sharing the action figures equally in their place circles. And so that's where we're going to really dive into van der Waal interactions. So nonpolar molecules like CH4. Carbon and hydrogen have pretty much the same electronegativity, same personality, and so they have a nice little place circle where they pass the electrons around, right? But even molecules like water has van der Waal interactions as well, and so the van der Waal interaction associated with water, right? So this idea that water molecules can attract or repel each other creates something called a hydrogen bond. So let's investigate hydrogen bonds first, okay? And then we'll go and investigate the nonpolar molecules. Okay. So hydrogen bond is this. When you have hydrogen bonded to an oxygen, the oxygen pulls most of the electrons towards it, okay? And that leaves the proton out there in solution exposed. So it's like a magnet, and it can attract negatively charged molecules. But it can also, right, attract another water molecule. So you have the positive end of one water molecule is attracted to the negative end of another water molecule. But we don't just see hydrogen bonds in water. We also see hydrogen bonds in DNA. And so what you're looking at here is, holy cow, this is I know it's a crazy picture, right? We're like, we go from like, here's a water molecule to a DNA molecule. What are all these things? Okay, so anyways, you have two strands in a DNA molecule. It's a double helix, right? So two strands that wrap around each other, and they're glued together by hydrogen bonds. And so over here, I'm just going to point out one of them and you'll see what I'm talking about. See, the hydrogen bonds are given by the dotted lines between the two strands, okay? And each one of these that are colored in green or purple, that represents one monomer or one subunit of a DNA molecule, okay? And so they zip together, these two strands of DNA zip together by hydrogen bonds. Up here on this adenine, right, we have nitrogen bonded to two hydrogen. Now, if you remember, anytime nitrogen, oxygen, or fluorine, or even sulfur are bonded to hydrogen, they are going to pull those hydrogen electrons towards them and leave an overall positive charge exposed out here. Well, over here on thymine, look, there's an oxygen double bonded to a carbon. So the oxygen is going to pull the electrons towards it, and it's going to have an overall negative charge. And I'm going to go ahead and just annotate this real quick. So you've got an overall negative charge here and an overall positive charge here, and they are attracted to each other. Like that's the hydrogen bond. So hydrogen bond doesn't actually share electrons. It's really more just a bond that's formed like two magnets clicking together. Okay, and so this whole strand is zipped together by hydrogen bonds. Okay. let's carry on. Get rid of my annotations. All right, so here's van der Waal interactions, London dispersion. So this is where we're talking about non-polar molecules. So the question is like, why are non-polar molecules able to dissolve non-polar molecules, right? And this is how. So let me explain what this figure is. Okay, it's super basic. The blue circle represents one atom. The red circle represents another atom. Together, they have a bond, and so they make a molecule. So these two circles represents one molecule. So here's one molecule, okay? And then here's a duplicate of that molecule. So remember, van der Waal interactions deals with how molecules of the same type attract each other or repel each other. So you have two molecules of the same type. Let's say these are nonpolar fats, okay? What they're doing inside of this molecule is the blue circle is playing with the electrons for a little bit. It's playing with the action figures, and then it passes it over to the red circle, and the red circle has it for the same amount of time. And then the red circle passes it back to the blue circle. So while these electrons are being shared in this split second, right, where the action figures get passed to the other player in the circle, right, it creates a temporary dipole. So maybe maybe this blue circle passes its electrons to the red circle for a brief moment in time, right? So the red circle's playing with them. It has this brief negative dipole for a second. Now, if there's a molecule next to it doing the same thing where the blue circle has passed its electron to the red circle, these two ends of the molecule, the negative end of the red circle and the positive end of the blue circle, attract each other and they can dissolve each other. And so this is why nonpolar fats can also dissolve other nonpolar fats. Okay, so always remember this because this will come in handy like for the rest of your life. Like dissolves like. Things that are polar, things that are ionic will dissolve in polar molecules like water, right? That creates the polar solvent, okay? Things like nonpolar stuff like fats, alcohols, stuff like that will be able to dissolve other nonpolar things. So that's why like alcohol becomes like a universal solvent because alcohol you can dissolve fats in alcohol. You can other nonpolar things like you can take oils and mix oils together, stuff like that. All right. Polar molecules can dissolve polars, nonpolar can dissolve other nonpolars, but polar cannot dissolve nonpolar, and that's an important thing to remember. And so that's why if you have a nonpolar fat molecule and you have a polar water molecule, you cannot dissolve them into each other. You take some oil, like a fat, and you take water and you dump them into the same container. They separate. They can't dissolve each other. So anyways, let's touch on functional groups. Let's touch on functional groups. Functional groups are, you can look at them like it's a molecule, like a small molecule that's attached to a bigger molecule that changes the personality and function of the bigger molecule. So it's sort of like you can think about functional groups as like modifications for a weapon, right? So you've got like your base M4 carbine or something, right? And don't get offended. I don't own any guns, so I'm just using this as an example. Not like some woohoo gun-toting hippie. Gun-toting hippie. That's not even a thing. Anyways, so you got an M4 carbine, right? You can put a sight on the M4 carbine, and that's going to change its functionality, right? You're not using the iron sights anymore. You're using the scope, okay? You can take and put like a laser, a nighttime laser beam on it, so you can like use it to aim at stuff at night. You can put on like an extra 30 round magazine in it. You can make it have a collapsible butt stock. There's so much that you can change and modify, but the actual M4 carbine stays the same. And so these functional groups are little molecules that we can attach onto bigger molecules and change the overall function of that bigger molecule. All right. And so just a couple of them, right? So the amino functional group is, oh, I should explain this. Okay. You're going to see an R, right? You're going to see a lot of R's in all of these. There is no element for R. That's why R is like being used here, and they're with good reason, right? R represents the bigger molecule. The R represents the M4 carbine in this example, right? The functional group, the NH2, that's like the collapsible buttstock, right? Or the M203 grenade launcher that you can attach to the M4 carbine. Okay, well, amino is not like a grenade launcher, but You get my point. So anyway, so you get the R group just represents the bigger molecule, right? The functional group that's attached to the bigger molecule is what gives it some personality. And so the amino group, right, the NH2, well, nitrogen's more electronegative than hydrogen, so it's going to pull the electrons towards it. And so that means these protons out here will be exposed, and so it'll give it an overall positive charge on that end of the molecule. Also, nitrogen has a lone pair of electrons that's not pictured here, which means that it can accept a positively charged proton, and sometimes you'll see this drawn as NH3. So sometimes a proton will come over and be like, oh, sweet, you got 2 electrons, I'll take those to pretend like I have full orbitals. And so it'll actually invite itself to the circle and play with them. Okay, carbonyl groups, okay? There's 2 different types of carbonyl groups. So this is where carbon is either bonded to, like, here's your M4 carbene. What do we do? Carbon's either bonded to like a M4 carbene on one side or both sides. So it's sort of like sandwiched here in the middle. And it's a carbon double bonded to an oxygen. We see ketones show up a lot. Like you've probably heard of like the keto diet, right? And that's when you only eat fats, you don't eat carbohydrates. And so this molecule, this C double bonded to an O, surrounded by, like a bigger molecule on each side, right? That comes from fats. Like, so when your body breaks down fats and makes ketones, your ketones can go to the mitochondria and create ATP energy. So it's good. So that's where the keto diet comes from, that molecule right there. Or aldehyde. So this is a carbon double bonded to an oxygen still, but it's got its M4 carbine just on the left, and over on the right it's got a hydrogen. And we see aldehydes when we break down sugars, like when we start to break down sugars, or during fermentation. So we'll see that a lot. Carboxyl group, so that's a C double bonded to an O and single bonded to an OH, or a hydroxyl group. And we see these with fatty acids. So the R group over here, the M4 carbene, often is a hydrocarbon tail. So that's what becomes a fat. But this little guy is a functional group attached to it. Hydroxyl is a M4 carbene attached to just an OH group. And so usually if we see this OH group, it gives it the function of an alcohol or a steroid, okay? Some amino acids also have that attached to them. Okay, a methyl group. So this is where you have, remember how I said methane was CH4, carbon wants that 4th bond? Well, that 4th bond is bonded to a bigger molecule, and so methane is just a CH3 attached to something. If you take methane, which we know is highly flammable, right? We know take methane, cow farts, you light it on fire, right? So we can take a methane and we can make a whole bunch of methanes and attach them to each other, and that's what actually makes a fat. A fatty acid or a fat molecule or a lipid is just a bunch of methyls just attached to each other. So this is why like fats have more energy than like sugars. Okay, anyways, phosphate group. So that's a PO4, and then see how it says 2 minus? That means that this this particular molecule has 2 more electrons than it should. Okay. And we see phosphates a lot. We see it in ATP, of course, right? Adenosine triphosphate, so it's got 3 phosphates attached to each other. We'll see it in a phospholipid in our next unit on our next PowerPoint on macromolecules. So we'll see phosphates a lot. So get used to this, right? Be able to identify phosphates, hydroxyls, carboxyl groups, amino groups. Those are ones we'll see a lot. Sulfate. Well, you see sulfates, they're in biology for sure. We don't really deal with them too much in intro bio. Yeah. And then here, do not get wrapped up with this. I just put this up just to show you that there are like way more functional groups in organic chemistry, and that's for like a junior level class in chemistry, right? But there's just so many different ones, and I just gave you a couple of basic ones. Okay, so let's talk about how we go from one molecule to many molecules. Like, how do they form together and make a chain, right? So let's say you have something like one Lego block, and then I want to make like a line of 10 Lego blocks. And so I take one Lego block, I join it to another one, join it to another one, join it to another one, and pretty soon I have a long chain of Lego blocks. That starts at a monomer. So a monomer is a single unit of repeating length. We're going to talk about monomers a lot. So that's everything that we talk about in this chemistry lecture, we do talk about a lot, and that's why I put it in here. I know a lot of it seems superfluous, but just trust me, we're going to talk about them. So a monomer, a single unit of repeating length. So a monomer could be something like just a simple sugar like glucose. And if you have glucose bonded to glucose, bonded to glucose, bonded to glucose, well, that's when we have a polymer, like a complex carbohydrate. So anyways, monomers can be a couple different things, and we'll see examples of these as we go forward, right? As we get into our bigger biological molecules. So monomer is just something of repeating length. So we see this a lot in amino acids. Like there's an amino acid bonded to an amino acid, bonded to an amino acid, and all together, when they're all bonded together, that makes a polypeptide or a protein. So if you've heard of branched chain amino acids, right? That's the idea that you have all these amino acids that are bonded to each other. All right, so it's a big long polypeptide, but they're of the same type of amino acid. So a branched chain amino acid might have a lot of leucine in it, and that's just leucine bonded to leucine, bonded to leucine, bonded to leucine. Glucose is another one that we see a lot, right? So glucose is a primary fuel for the body, primary fuel for the brain, primary fuel for most living organisms, right? Even cats who are obligate carnivores, right, who only eat meat, their body can take glucose, or sorry, their body can take the amino acids, the protein from the meat that they're eating, and it can convert it into glucose. So we see a lot of glucose. Every organism uses it. And to store glucose, you bond glucose to glucose to glucose to glucose to glucose, and you form a starch like glycogen or something like that, or amylose, or potato starch, that kind of stuff, right? It would be a bunch of glucoses bonded together. Fatty acids, right? That's the monomer of a lipid, right? So lipids or fats are all made out of fatty acids. Nucleotides, that's DNA and RNA, right? Those are they're monomer subunits, which um, get bonded to each other to make a polymer. And so polymer is just a chain of repeating monomers. And so what I've done is I've shown you, like, okay, we have amino acid as a monomer. If you have a bunch of amino acids bonded together, that makes a protein. We have glucose as a monomer. If you have a bunch of glucose bonded together, that makes a starch. You have fatty acids, a bunch of fatty acids bonded together makes a lipid, or a triglyceride, or a phospholipid. Nucleotides bonded to each other can make something like a DNA double helix. Okay. So when we combine two monomers together, we have to do a certain type of reaction. We have to remove a water molecule. Half comes from one molecule, half the water molecule comes from one monomer, and half the water molecule comes from the other monomer. And then the two monomers are able to join each other, join together in their little place circle once they've removed the action figures that were water molecules. When we take a polymer, like a long chain of repeating monomers, and we want to break them down into monomers, that means we have to take a water molecule and split it up and then attach that water molecule to each monomer as we break them off of the polymer. And I'm going to show you an image of this, right? So dehydration is where you remove a water molecule in order to bond two monomers together. Hydrolysis is where you cut a water molecule in half to attach it to two monomers that you've just separated from a bigger polymer. So let's take a look at this one, right? So this is just um, a pictorial image of going from monomer to polymer, a dehydration reaction. So let's just start over here on the left, right? So don't get wrapped up in all the stuff over there to the right. So what you have here on the left is you've got glucose. Here, I'm going to annotate for a little bit. All right. So you've got glucose. I don't know if oh, that didn't work here. Sorry, still trying to figure this out. I think I can move this annotation box over there. Okay, so this molecule right here, that's like a glucose molecule. And glucose has a functional group of a hydroxyl group attached to it. It's also got a free hydrogen on the other side. So that's a glucose. That one's a glucose. So we've got a glucose here, a glucose here. And if we want to bond the two glucose molecules together, we're going to take the hydrogen from one, the hydroxyl from the other, and we're going to pull, we're going to to pull them off and make a water molecule. H2. So that becomes water. And what ends up happening is you can see, let me just, as you can see right here, this bond that's bonded to hydrogen, and right here, this bond that's bonded to the hydroxyl, those are actually going to form a bond to each other. So when the water molecule gets removed, right, that bond right there was this bond right here. So this molecule of glucose and that molecule of glucose bind together, and now you've got a polymer. But now look, wait a second, we want to add another monomer of glucose right here, right? And so that monomer is going to come in. We're going to take off this hydroxyl group. We're going to take off that hydrogen, and both of those are going to turn into water. And now we've got 3 glucose molecules. And then same thing. So if we want to add another one, right, these two, the hydroxyl group and the hydrogen pop off, turn into water. And then we've got 4. So that's how you make a polymer. And polymers can be endlessly long. Now it's important, because we're going to talk about energy in the next unit, to remember that this reaction is a building reaction. This reaction, right? Because we're going from individual pieces of Lego into a big tower or something, right? A big polymer of Legos, right? And so it's endergonic, meaning it requires energy to come into the system, or anabolic is another way to think about it, right? Anabolic steroids are building, right? You shoot them into your body and you lift a bunch of weights and you get huge and just jacked, right? So endergonic, anabolic, these are all building reactions that requires energy to come in from an outside source. And so typically that outside source is going to be an enzyme. And we'll see more of that next unit. So the next reaction that we see is from polymer to monomer. How do we break things down? So if we have 4 glucose molecules and we want to pop one off, what we need to do is we need to take a water molecule and we need to split it, okay? And we're going to split it, and we're going to attach one hydrogen. We're going to attach one hydrogen here, right, where we're separating this molecule off. So we pop this molecule off, right? We attach one hydrogen from the water onto the remaining 3, right? This is the remaining 3. So we take one hydrogen from the water and attach it there. The OH group from that water molecule gets attached onto the glucose molecule that just popped off. And then that way we have that free glucose molecule. And then we now have only 3 glucose molecules in our polymer. And then same thing. So a new water molecule comes in, it gets split up, right? Half of it's going to get attached there. The other half's going to get attached there. And then boom, another monomer floats away. Now you have another water molecule come in. Half of it's half of it gets attached there. The other half gets attached there, and so on and so forth. And so we have to split water in order to make monomers from polymers. And so remember, this reaction is exergonic, meaning that it goes from a state of high order or high complexity into a state of simplicity, and simplicity and equilibrium, if you will, right? Because you can't break I mean, you can break one glucose down. It takes a while, but you can't like break this down any further. It's already in its constituent form. And so the starting molecule that has 4 glucoses attached, the starting polymer, is in a higher energy state. Whereas when it gets broken down and all these bonds release their energy, it will then be in molecule. And then not be things where they have the same level of electronegativity. They share the electrons equally, and they do not behave like a magnet. Unless, of course, they're in a solution with other molecules like themselves, then due to van der Waal interactions, they can actually dissolve each other. Okay, remember, like dissolves like. I'll bring that up a lot. And then ionic bonding is this idea that when you take an ionic bond like sodium chloride, something that's very, 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 very different in electronegativity, and you drop it in water, the water is going to pull them apart. And then depending on what they are, if it's a cation and it has a positive charge, the negative end of the water molecules will kind of surround it and separate it from the chlorine. The chlorine is going to gain the electron from sodium, so it's got a negative charge. It's an anion, and then the positive ends of the water molecule will surround it. So that's ionic bonding. Okay. We already know that water has many properties: cohesion, adhesion, it loses density, it has a high heat capacity. I forgot to mention that. It has a high heat capacity, it's not in here. But that means like if you heat up water, it stays hot for a long time. If you cool water off, it stays cold for a long time. It holds on to its temperature. Okay. And then we also know that functional groups are like little attachments that you can add onto a weapon in Call of Duty or something, right? You can attach your scope or your silencer, right? Functional groups determine the personality of the molecule. So if you have an M4 carbine, you put a big, huge scope on it, a long barrel and a silencer. Okay, well, now it became more like a sniper rifle, right? Or if you take it and you shorten the barrel and you put like a quick release mag on it and stuff like that, okay, now it's become more like an assault rifle. So it's like these functional groups can be attached to the bigger molecule and they change the personality of it, like how it can interact with other things. We know we do dehydration reactions to turn monomers into polymers, and then we know we do hydrolysis reactions where we split water to break down polymers into monomers. And remember, dehydration, going from monomer to polymer, is a building reaction. Right? It takes energy from an outside source to build these things into polymers. Hydrolysis reactions, those happen spontaneously. They break down, right? Going from something complex to simple, right? And that's exergonic for hydrolysis. So exergonic or catabolic. Okay, and that's it. I'll see you guys for the next lecture. Bye.